Hi, I'm Jim Young Kim from Seoul National University. Today, I'm excited to present our work titled ReFlex, Text-Guided Editing of Real Images in Rectified Flow via Mid-Step Feature Extraction and Attention Adaptation, which has been accepted to ICCV 2025 as a highlight paper. This work addresses a key limitation of existing image editing approaches. Most of them are designed based on features from UNet-based diffusion models, which makes it difficult to apply them to the recently popular MMDI-based rectified flow models. To overcome this limitation, we analyze the internal features of MMDIT and introduce a new method that enables text-guided editing of real images within the rectified flow framework. Previous image editing methods, such as prompt-to-prompt and plug-and-play, were primarily developed based on the analysis of UNet-based text-to-image models, which were the dominant architecture at the time. These methods first identified internal UNet features that capture the structural information of an image, then extracted those features from a given source image and injected them into the generation process of another image to perform the desired edit. However, recent high-performing text-to-image models have moved away from the traditional UNet architecture and instead adopted a new design called the Multimodal Diffusion Transformer, or MMDIT. This architectural shift makes it challenging to directly apply previous image editing methods to these new models. In this work, our goal is to overcome this limitation and develop an image editing method tailored to the MMDIT architecture. To achieve this, we first conducted an in-depth analysis of MMDIT, focusing particularly on its joint self-attention mechanism and residual connections. We analyzed MMDIT by directly visualizing specific features extracted during the image generation process and by injecting those features into the generation of another image to observe their effects. To investigate the behavior of MMT's joint self-attention, we divided it into 4 components based on the modality of the query and key. Through this analysis, we found that attention maps where the query belongs to the image part, namely the image-to-text cross-attention and image-to-image self-attention, carry meaningful structural information about the image. We therefore defined these 2 as the key features of the joint self-attention. We also analyzed the residual connections in MMDIT. Specifically, we divided them into 2 components: the residual feature computed within the current layer and the identity feature carried over from the previous layer. Our analysis revealed that the residual feature effectively captures the structural information of the image and can be utilized for editing, whereas the identity feature also contains appearance details, making it less suitable for editing purposes. Although we analyzed the internal features of MMDIT, extracting these features from a real image is not a trivial task. Typically, features are obtained by inverting an image into the noise space and then reconstructing it back to the original image. However, rectified flow models are known to have poor reconstruction ability after inversion. When the reconstructed image deviates significantly from the original, the extracted features fail to retain meaningful information about the source image, and consequently, the generated results based on those features also differ greatly from the original. To address this issue, we analyzed the intermediate latents obtained during the inversion process. We found that when an image is fully inverted into the noise space and then reconstructed, the original content is almost completely lost. In contrast, when the inversion is stopped at an intermediate step and then reconstructed, the original image can be nearly perfectly preserved. Based on this observation, we propose mid-step feature extraction, where features are extracted from the latent at this intermediate inversion step. After extracting features from the real image, we propose 2 attention adaptation strategies to effectively inject them into the target image generation process. The first is called I2TCA adaptation. The goal of I2TCA adaptation is to inject the image-to-text cross-attention I2TCA features extracted from the source image into the target I2TCA in a way that preserves the structural information of the source while improving alignment with the target text. We consider 2 cases. If a token in the target text matches a token in the source text, we replace the target I2TCA of that token with the corresponding source I2TCA. If there is no matching token, we do not inject the source I2TCA, but instead scale up the target I2TCA by a factor greater than 1. For example, if the source prompt is a goat and a cat, and the target prompt is a horse and a cat, the token cat in the target prompt is directly matched to the token cat in the source prompt, so we inject the corresponding source I2TCA into the target. In contrast, the token horse has no matching token in the source prompt, so we scale up its target I2TCA instead. Through this process, regions that should remain unchanged are preserved, while regions that need to change are emphasized, allowing the final image to maintain structural consistency with the source and achieve better alignment with the target prompt. The second method is I2I assay adaptation. We observe that when the target prompt requires structural changes, directly injecting the source image to image self-attention into the target I2I assay causes the source structure to be overly preserved, preventing proper editing. To analyze this issue, we visualize the I2I assay maps for 4 queries marked as crosses on the image, using both linear and logarithmic scales. From the linear scale visualization, we found that each query's attention is excessively concentrated on a few neighboring pixels. At the same time, the log scale visualization revealed that each query's attention also captures the overall structural information of the entire image. Based on this analysis, we designed the following technique. Our method replaces the excessively concentrated top K attention values in the source I2I assay with the corresponding values from the target I2I assay. This allows us to prevent the local structure from being overly preserved when injecting the source I2I assay while still maintaining the overall structural layout of the source image. Lastly, for local editing, where only specific regions of an image need to be modified, we generate an editing mask to precisely localize the editable area. To construct this mask, we make use of the blended word provided by the user. Specifically, we compute the image-to-text cross-attention map corresponding to that blended word, then apply Gaussian smoothing followed by Otsu's thresholding to obtain a binary editing mask. Finally, we adopt a technique called latent blending to ensure that regions outside the mask remain unchanged, while only the intended areas are modified in the final result. This slide shows an overview of our final method. This slide shows the performance comparison on the Pi benchmark. As you can see, our method successfully edits the image according to the target prompt. For example, transforming a heart into a circle, a person into Iron Man, or changing the color of a flower, whereas the other methods fail to follow the given target prompts accurately. This slide presents the performance comparison on the Wild TI2I Real benchmark. As shown, our method is the only one that successfully modifies the images in accordance with the given target prompts. This slide shows the quantitative results. Our method outperforms all previous approaches by a large margin, not only on the conventional metrics, but also in human evaluations. This slide shows the results of our ablation study. We can see that mid-step feature extraction plays the most critical role in preserving the structural consistency of the image. In addition, both attention adaptation techniques significantly contribute to improving text alignment. Thank you very much for listening to my presentation.